Okay, so you have atoms here. You have atoms here. Okay. So if they are falling with theta, okay, and say this is the perpendicular, and if you say this is my k wave vector, incoming wave, okay, and this is my deflected wave k is equals to 2 pi by lambda. Okay, similarly your k dash is equals to also 2 pi by lambda. Why? Because this is the inelastic scattering. X-ray is elastic scattering. Okay, so X-ray is elastic scattering. Elastic scattering, that means the magnitude of k and k dash is same. Okay, so if I say this magnitude of k is 2 pi by lambda and magnitude of k dash also 2 pi by lambda. Okay, and now we know the Bragg's law is what? If we solve this one, we know the Bragg's condition. Bragg's law is 2d sine theta equals to n lambda is your Bragg's law. Now similarly, if we if we write this same law in the reciprocal lattice, okay, so reciprocal lattice, this law comes out 2kg upon, what is the formula? It is the formula for, if I write the Bragg's conditions in reciprocal lattice, okay, where the angle between k and j is pi, okay, and your phi is nothing, that is your pi by 2 minus theta. So if I write this here, if I say this is my, this is the planes, okay, and the vector which is perpendicular to this plane is called your reciprocal lattice vector. Okay, now if I say this is my g, this vector is g, okay, and if I connect these vectors here, so obviously this is my k, this is my k, and this is my g, and this is equal to g, k dash. So I can write my k dash is equals to k plus g. Okay, so if you take a square, you will take magnitude square, k dash square equals to k plus g whole square, and this will give you k square is equals to magnitude square k dash square. Similarly, this will give you k dash square plus g dash square plus this will give you 2kg, okay, or 2kg, simply 2kg, okay. And now since k dash is equals to k, okay, this will be cancelled out. Okay, so you will end with 2kg, okay, 2kg plus g square, okay, g square equals to 0. Now you can replace g with minus g also, so you can also write this expression as 2kg equals to g square also. So when you write the formula, okay, only important thing you should remember, the angle between k and g is phi. Okay, so this is the same thing. You can bring this reciprocal space, and this is your direct lattice. So you can convert these two things. Okay, so if you write here, you can write this is 2k Okay, K, G, this is your cos of phi, and this is your G square. Okay, G square. So this G cancel. Okay, you have only G left. So this will be your cos phi will be your G upon 2K. Okay, and now you know what is G. So G is what? Basically your G is 2 pi by 2 pi dHKL. Okay, so you can write here, this is be your G will be 2 pi upon dHKL, and this is 2 twice, and you have this K is also 2 pi by lambda. So this 2 cancel, pi cancel. Okay, and here cos pi you can write cos 90 minus theta. Okay, pi is 90 minus theta. This will give you sine theta. So sine theta is equals to, now you left with how much? You have here 2 cancel, pi cancel, 2d. Okay, so lambda upon 2d. And if you solve this one further, okay, this will give you same expression like Bragg's law. So this both are equivalent. So you should remember both the formulas in your reciprocal lattice back condition as well as in this direct lattice, the direct space. Okay, any doubt? मोनिका, इसमें कोई डाउट है?
No, sir. Thank you.
Okay. Now, so your X-ray diffraction follows your Bragg's law. Okay. Now, the X-ray intensities. Okay. Intensities of X-rays. We'll talk about intensities of X-rays. So, intensities of X-rays. Okay. So intensities of X-rays HKL is basically is given by FHKL. Okay, and FHKL is a structure factor. Okay, whose value is given by, what is the formula for HKL? Tell me. What is the formula for HKL? Anyone? Okay, that is Fj. J is number of atom and their fractional coordinates, e power iota 2 pi. Tell me, what should I write? Hx plus ky, h plus ky plus lz, where this is xz, yz, zz. So xz, yz, zz are fractional coordinates. Okay, fractional coordinates. Now all the peaks, you know, there will be extension of X-ray intensities. You won't get all the peaks for all the structures. Okay. Now, if we see for simple cubic structure, if I make a table, okay, absent peaks. Okay. If I say absent peaks, so if I take simple cubic structure, okay, so your system, and if you simple cubic, and if I say here say diffraction peaks, diffraction, okay, so all diffractions are present, all deflection, all peaks are present, all diffraction peaks are present, all peaks are present, all peaks are present. Okay, in simple cubic. If I say BCC, only those peaks will be present for which H plus K plus L are even. Okay, if I say FCC, okay, only those peaks will be present for which HKL are unmixed. Okay, HKL are unmixed. That is either your HKL should be odd or HKL should be even. Okay, like you have a 1 1 1 type of peaks or 0 0 2 type of peaks. 0 is considered even. Okay, so the HKL should be unmixed for FCC structure. Okay, so similarly, if I say it's a diamond, okay, so diamond, which peaks will be present? Can anyone tell? Diamond has a which kind of lattice? Diamond के पास कौन सा lattice है? Diamond is like also FCC lattice. Okay, so HKL should be
H plus K plus L should be divided by 4.
Yes, so HKL should be unmixed. Okay, unmixed means either HKL should be odd, or if they are HKL even, then H plus K plus L should be divided by 4. For example, if I give a question, now I given you 4 system. Okay, so which of the following reflections are present in all these systems? Okay, so if I give you 2 2 0, 3 1 1 and 4 0 0 and 3 3 1. Okay, so can you tell me which of the reflections are present in simple cubic, BCC, FCC and diamond out of
So
these?
the first one, 2 2 0.
This will be present in diamond. Okay, this will be in diamond. So if I get diamond 220 will be in diamond, and which one will be present in diamond? Tell me other things.
4 0 0.
4 0 0. What about this one?
That is for FCC only. FCC and SC.
Why not for this diamond? Why not for diamond?
Oh, diamond is also present because
Diamond,
this
is odd. Okay, diamond also present, and this is also present for diamond also.
Yes.
Okay, for diamond you should have either this should be odd. Okay, so this is odd, and and if it is even, should be divided by 4. So this is divisible by 4. So all the 4 deflections are present in diamond. Okay, if I talk about the FCC mein, which are present in FCC? FCC should be all, yes or no? Which is not present in FCC? Tell me.
Every crystal is present. 220 is present. 311 400.
Okay, so obviously FCC also all present. Okay, all this same thing present. BCC only 220 will present and 440 will present, and simple cubic you have all. Okay, simple cubic you should have all. So let me check whether for FCC everything is present. 220 is present in FCC. Okay, then 311. What about 311? 311 is present in FCC? You should present, na?
Yes, sir.
Okay. Now, so that loss you should remember for exam. Now, if you have been given X-ray diffraction pattern of some material, okay, how to identify whether it is a simple cubic, FCC or BCC? Okay, so just by mere observation, you can find, okay, whether this system is your simple cubic, FCC or BCC. Okay, for that you need to see their peak positions and their HKL value. So suppose if I'm writing the HKL value. Okay, and I'm writing there H plus K plus L, and I'm also writing H square plus K square plus L square values. Okay, so suppose HKL is your 100, first plane is 100, second is what 110, third is your 111, Okay, fourth is what? Fourth is your 2, 0, 0, then 2, 1, 0. Then you have a 2, 2, 1, 0, 2, 1, 1. Then you have a 2, 2, 0, and then you have 2, 2, 1. Then you have a 3, 0, 0, 3, 1, 0, 3, 1, 1, and 2, 2, 2, 3, 2, 0, 3, 2, 1, and 4, 0, 0, and then you have a 3, 2, 2. Okay. So let us sum this one. So this will give you 1, this will give you 2, this will give you 3, this will give you again 2, this will give you 3, 5, 4, 5, 3, and then this will give you again 4, 3, 1, 4, 5, 6, 5, 5, 1, 6, and this is 4, and this is 2, 2, 4, 7. Okay. If I take this h square plus k square plus l square, this will give you 1, this will give you 2, this will give you 3, this will give you 4, this will give you 1 square 1, 1 to 5, and this will give you what? 1, 1, 2, 1, 1, 2, 2, and 2 and 4, 6, and this will give you how much? 4, 8. This will give you 8, and this will give you 9. 7 is not present. Okay, 7 is not there. You have to remember. Then this will give you 9. This also give you 9, and 3, 1, 0. This give you 10, and this will give you 11. This is 4, 4, 4, 12, and this give you 2, 9, and 4, 13, and this is 9, 9, and 4, 13, and 14, 14. Then you have 16, 15 also not there, na? So 3, 2, 4, 4, and 9, 13, and then you have 3, 9, 4, 13, 1, 14, and then you have 16, and then you have finally you have 2, 2, 4, 9, 4, 13, 17. So now I know that my for cubic system, my DHKL, d sin 2d sin theta, 2d sin theta is equals to lambda. Okay. So if I write my sin theta will be simply lambda upon 2d, and if I take sin square theta, that will be my lambda square 4d square, and my lambda d square is nothing. D square is what is value? A square h square plus k square plus l square. Okay, so these are the constant for given system. So your sin square theta will be proportional to your h square plus k square plus l square. Okay, now suppose you have a extra diffraction pattern. Okay, you have been given extra diffraction pattern for the intensity. Okay, now you know these peak positions. Okay, these peak position you know, and the HKL of HKL also you know. Okay, now what you can do, you can just measure sin square thetas. You can find a sin square thetas ratios of these peaks. Okay, for example, if I now take simple cubic, okay, if I take simple cubics, so simple cubic, these all planes are present. These all planes are present. So if I take the for simple cubic, if I take the ratio of ratio of h square plus k square plus l square, or sin square theta for simple cubic, okay, the ratio will come out 1 is to 2 is to 3 is to 4 is to 5 is to 6 is to 8 is to 9, so on. Now you have extra diffraction pattern, and you know theta's value. You take the ratios of these theta's value. If this matches with this one, then your system will be simple cubic. Okay, yes or no? Can you do like this? if you have if your X-ray diffraction pattern is given and 2 theta value is given to you, now you find the ratio of these theta sines. You find this theta from this 2 theta, out of 2 theta, you find first theta, and then you take sin square theta ratio for these given peaks. If this ratio comes out 1:2 plus 3:3, that means all the peaks are present, then you can simply say this is your simple cubic, your system is simple cubic. Okay. Now suppose BCC, if I talk BCC, so BCC, all the planes are not present, so this will be present in BCC. Okay, or H plus KL should be even, this will be present in BCC. Then 220 4 211 H plus KL is even, this will be present. Then this will be present. So if I take the ratio for BCC, this will come out 2:4:6:8:10:12:14:6:16, or 1:2:3:4:5:6:7:8. So if ratio is coming like this, you can identify that system is your BCC. Okay, here 7 is not there, here 7 also is there. So by calculating the sin square theta's values, okay, you can tell which structure is what type. Okay, so similarly, if it is FCC, okay, so FCC, only those peaks will be present for which you are where they are unmixed. So this is mixed, this is mixed. So first peak will be in FCC, first peak will be 111. Okay, and 111 is H square plus K square, L square is 3. The ratio will be 3. What is the second peak? What is second peak? Tell me.
200.
200. So 200 H square plus K L square is 4. So it will be 4. Third will be 220. So it will be 8. Okay. So and similarly, if you write fourth peak will be your
310 then.
3111.
Sorry.
3111. So what will be 9, 10, 11. Okay, 11. So this will be like this. This ratio will be like this. Okay. So this way you can just by observing, you can tell which structure is what kind. Okay. Now, Jan was asking about KCl structure.
Yes, sir.
So NaCl and KCl basically NaCl is FCC structure. Okay, and your KCl also FCC structure, but there is a slight difference between X-ray diffraction pattern of KCl and your this one NaCl. Let me draw that one. Okay, so one question also came in exam. So if I draw the KCl, okay, so I'm going opposite. Okay, so this is my KCl peaks. This is the intensity. Okay, this is 2 theta. Okay, so I'm going like this. So this is the 2 theta values. So first peak for KCl is 200. Second is 220. Then you have a 222, and then you have a 400. Okay, then you have a 420. 420. So 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay, 420. So this is the X-ray diffraction of KCl. Okay, X-ray diffraction of KCl. Now your KCL is basically FCC, but if it is FCC, then the first peak should be 111. Yes or no? First peak should be 111.
Yes, sir.
And second peak, 2.200. Third peak is 220. Okay. And other things are fine, or yes or no? Other things are fine. So it should be 3. First should be 111. Then should be 200. Then
So
should
odd
be
number of HKL values are not present. 311.
So odd numbers are not present in the case KCL. Okay, like 311 is not present, 11 is not present. Okay, so now why 111 is not present? Okay, so 11 peak, if you see in NaCl and even in the KCl, or you see potassium bromide, generally this 11 peak is very small peak, and the peaks which is corresponding odd on a 311 odd number, those peaks are generally very small peaks. Now those peaks get disappear in the case of KCl. Okay, why? Because your K and Cl, potassium and chloride, both are isoelectronic. Both are isoelectronic. Isoelectronic means now both have same electronic configuration like argon. Yes or no? Okay. Argon is 18, so K plus is also 18, and Cl minus is also 18. So both have a argon type of electronic configuration. Okay. So now because both are isoelectronics, okay. So now the diffraction barely depends on electron cloud. How many electron clouds are there? So both have same intensity. Both atoms have same scattering power. But because both have a same scattering power, in X-ray diffraction they cancel out each other whenever there is an odd number, or this FCC odd is there. Okay. So when the FCC odd is there, this 311, 111, 3111, these atoms get their diffraction peaks get cancelled out because of symmetry. Okay. Now you get only 200, 220, 220, 40, 420. Okay. Now if you see this 220, 200, okay. So 200 is same like your 100. 220 is like a 110. This is your like a 111. This is like your 2000, and this is like a 21210. So basically these peaks are of simple cubic. So whenever so for KCL, X-ray sees KCL as a simple cubic structure, okay, with the lattice constant of A/2. Are you getting my point? See, this structure is a lattice constant, you are in A. Okay. Now if you see simple cubic, because your d sin theta is what? 2d sin theta is equals to lambda. Okay. So if I send d here, so d will be what? 2 sin theta. So sin theta basically will be your lambda upon 2d. Okay. And 2d is what? D is your a upon h square under root h square plus k square plus l square. Okay. Now if you say this is A/2, so 2 can go here, okay, and 2 can go inside. So either I write 100, so that will be 2a, you are 1 square 0 0. Okay, so you get, if it is a 100 peak, I can write this a. Okay, so this will be same, or I can say this is my lambda by A/2. So I can write a here, 2 here, and that 2 can go inside. Okay, and then become what? 2 will go inside and become 4. Huh? Or if I take this 200 peak, if I say this is 200 peak, then this will be 4 plus 0 plus 0, and if you solve this one, this 2 will come out here. Okay, so I can see, so this become basically A/2. Are you getting my point? See, if this is your sin theta. Okay, Now, if you're writing peaks as a 200, 220, 220, what will come? Always some factor of 2 will come. If I write 200, if I put here, then will come 2 lambda 2a. Okay. If I take 220, what will come? 4, 8, 4, 4, 8, 8, 4, 8 means 4 into 2, 2 root 2. So this comes 2 into 2 root 2 root 2, 2 root 2 lambda upon 2a. So this can be considered as a lambda upon 2. 2 I can send here, a by 2, and similarly this can be considered root 2 lambda 2 a by 2. So X-rays, basically when you find the X-ray on KCl crystal, for the X-ray this KCl is just like a simple cubic with a lattice constant of a by 2. That you have to do to remember. It's FCC, but X-ray sees this structure like as a simple cubic. Okay, so that's why you get all the peaks. You get all the peaks of simple cubic. Okay, if you make is A of FCC in a by 2 in your simple cubic. So that's why this is the difference. Okay.
So then we write FCCR, which is yes.
No, you have write to FCC. This is not BC, not BCC. BCC is not. This is the simple cubic.
Yes, sir, SC. Yeah.
So you write FCC. The structure is FCC. Okay, but for X-rays, okay, you can assume that they are saying like that this is a simple cubic. Okay.
So this is only for KCl.
This is only for KCl.
Okay, means other NaCl or other
they are all
known
FCC.
crystal lab.
They
111.
one peak will be there. One peak will be there.
Okay.
And this is one peak will be there. Okay. So now this was your, how much time is left? Okay. X-ray diffraction. Okay. Now you have reciprocal lattice. Okay. Reciprocal lattice. So in reciprocal lattice, okay, if you have been given a direct lattice R and A1 plus M A2 plus N A3, okay. So its reciprocal lattice G will be given. So the reciprocal lattice will be basically Fourier transform of this R. That will be your I G dot R. Okay. So the lattice which satisfies this condition, either this condition or G dot R equals to 2 n pi, where n is equals to 0, 1, 2, 3. Those lattice is called reciprocal lattice. Okay. So Fourier transform. Okay. Fourier transform of direct lattice. Fourier transform of direct lattice is your reciprocal lattice. Is your reciprocal lattice. Okay. So the wave vector which satisfied this condition will form your reciprocal space. Okay. Reciprocal space is like nothing like a K space or momentum space. Okay. So the Wigner's lattice cell of direct lattice or a reciprocal lattice, okay, is called what? What is the Wigner's lattice cell of reciprocal lattice? It's called your Boolean zone. So now, if you want to discuss reciprocal lattice, okay, you need primitive lattice vectors. Okay, you need primitive lattice vectors. Okay, so primitive lattice vectors. Okay, so before that, just now I told you that a lattice given by G, if you satisfy this condition, okay, will give you the reciprocal lattice. And G, you know what is G? G will be your what? A star H K, or A, if I write R equals to N A1 plus M A2 plus L A3, then this will be H A1 star plus K. K is what? A2 star plus HKL. that will be A3 star, A3 star G. Okay. And what is the value of A1, A2, A3? So A1 star will be what? Tell me what is the value of A1, A1 star?
Ax cap,
A
x cap.
X cap. Tell me, Shan, what is the formula?
Set to A2 cross A3
A2
by 2 pi into A1 dot A2 cross A3.
into V, yeah, volume.
Into V, yes.
Yes. So this will be A1 dot A2 cross A3. This is the volume. Okay. Similarly, if I want to write A2 star, that will be your A3 into A1. A3 into A1, 2 pi. This will be volume will be same. A dot A2 cross A3. And similarly, if you want A3 star, you will be A3 will be what? A1 cross A2, 2 pi volume, or A1 dot A2 dot A3. This will be your reciprocal lattice vectors. Okay.
So 2 pi will be numerator, no?
Numerator, very good. 2 pi will be here. 2 pi will be here. This is 2 pi here. Okay. Now here, what I'm using this A1, A2, A3, they are primitive vectors. A1, A2, and A3 are primitive lattice vector. Are primitive lattice vectors. Okay. So in order to find the reciprocal lattice, you should know the primitive lattice vectors of different Bravais lattices or crystal structures. For example, if I write simple cubic, okay, for simple cubic, primitive lattice vectors, primitive lattice vectors, okay, for simple cubic, they are what? A1 is what? Ax cap, A2 is Ay cap, and A3 is your Az cap for simple cubic. If I use BCC, okay, my A1 will be what? Tell me.
A
Radhika?
by 2 I pi.
A by 2 X cap
Minus x cap.
minus X cap.
Yes, sir.
No, sir. X cap plus Y cap minus J cap.
Minus Z cap. A2 will be A by 2. Okay, so if X is there, now Y is there, minus X cap plus Y cap plus Z cap. If A3 is there, this will be A by 2 X cap minus Y cap plus Z cap. Okay, so this is for BCC. And this is the one set. For BCC, you have two set. Okay, also you can write for BCC, you can also write A1 is equal to AX cap. Okay, A2 is equal to AY cap, and A3 you can write A by 2 X cap plus Y cap plus Z cap. Both you can use. Similarly, if you have a FCC, okay, now you know the reciprocal lattice of simple cubic is simple cubic, the reciprocal lattice of BCC is FCC, and the reciprocal lattice of FCC is BCC. Okay, now if you write for FCC, okay, for FCC, what will come? Your A1 will come what? A1 will come A1, A2, A3. Okay, what is the value? Tell me.
A by 2,
A by 2,
y cap plus z cap.
Y cap plus Z cap, right?
Yes.
Y cap plus Z cap, A by 2, then
Z cap plus
X cap, and A by 2,
x
and you
cap
have
plus
X cap plus Y cap. Okay, these are for FCC. Okay, similarly, you have a hexagonal system. Hexagonal. hexagonal system. Okay, so hexagonal systems, you have number one type of is your A1. Okay, you have a √3/2 A x cap plus A/2 y cap, and your A2 is minus √3/2 A x cap plus A/2 y cap. This is for your, and your A3. What is A3? What is A3 for hexagonal? You can write simply 𝐶z cap. 𝐶z cap. Okay. Or instead of this one, you can also use second type of thing. Okay, where you have A1 is same like this one, √3/2 x cap plus A/2 y cap, and A2 you can use AY cap, and A3 you can use 𝐶z cap. This for hexagonal. Okay. Then you have also graphene. Okay. You have graphene also. Now, if you take simple cubic, okay. Now, next is graphene. Okay, graphene. So, what is the formula for graphene? Can anyone tell? What is the A1 for graphene? So, for graphene, you can write A1 is √3 A/2 √3 x cap plus y cap, and √3 A/2 √3 x cap minus y cap, and A3 you can use simply Z cap. One Z cap. This for graphene. Okay. Now, if I take simple cubic now, okay, for simple cubic, okay, your volume of the unit cell in direct lattice volume is given by A1 dot A2 dot A3. Okay, for simple cubic, if you put the value of A1, A2, A3 here, what you get? You get A cube. Okay, for direct lattice, for direct. Similarly, if you calculate now for volume for reciprocal lattice, okay, reciprocal lattice, okay, that you know the relation between this and this, the volume of reciprocal unit cell is given by 2 pi cube upon V. Okay, so the volume of unit cell or primitive unit cell will be now your 2 pi cube, that is 8 pi cube upon A cube for simple cubic in reciprocal space. Similarly, you can calculate for other things also. Okay, so this is V, okay, and this is V star, reciprocal lattice. Okay, similarly, if you write for BCC, okay, so BCC, your V is what? V comes out A cube by 2. Because BCC you have 2 atoms. Okay, so the volume for one atom is A cube, 2 atom is A cube, so volume for one atom is A cube by 2. Okay, similarly, if you say in reciprocal space, that will be what? 2 pi cube upon A cube by 2. So that will be now your 16 pi cube upon A cube. Similarly for FCC, okay, your V is, you have 4 atoms, so volume for one atom is EQ by 4, and your V star will be your 2 pi Q upon what? 2 pi Q upon A cube upon 4. That will become 32 pi cube, 4 into 8, 32 A cube. Similarly, if I calculate for graphene, okay. So graphene, this, how much is volumes comes? Tell me for graphene, what is the volume? Can anyone tell me what is the volume for graphene? Okay, so if I say for graphene, this comes out 3√3 A square by 2. Okay, and if I calculate V star, that is comes out 2 pi cube upon this V, that is comes out 16 pi cube 3√3 A square. Okay, so those results you have to remember.
सर
हाँ,
ग्राफीन में हम वॉल्यूम कैलकुलेट करते हैं या एरिया?
वो तो एरिया निकालते हैं हम लोग, एरिया निकालते हैं, बट हम लोग के A3 को 1 ले लेते हैं ना, जेड कैप ले लेते हैं, जेड कैप, तो सेम ही आएगा, निकाल के देखो सेम ही आएगा. So if you are saying instead of 2 pi q, I should put 2 pi square here, na? So just check it. Just give me 1 minute. Just check the class notes whether it is matching or not matching. Answer is matching or not. For graphene. Okay. So if I put this 1, this should be basically area. Okay. So it is 4 pi. It's coming 8 or 16. Just check it in the notes.
8, sir.
8. It's coming 8, na?
Yes.
Okay. So you write here.
No, in class we have calculated the area, so that's why there was 8.
So here pi square is there.
Yes, sir.
Okay. Pi square and then 8.
8 pi square, yes.
This is correct.
1, 3,
This is correct. This is correct. Okay. So this is basically, and this is same, na? This is same. This is same. 2 pi square. This should come. Now what you can do, you have, I'm giving you homework. Okay. You have this, I given you the primitive lattice vector. Okay. You find out A star, A2 star and A3 star for graphene. For graphene. Okay. And now calculate the volume. It should come like this. Find out this one and calculate this one. This should come like this. Okay. Otherwise, I will discuss it tomorrow. So I'm stopping here. Okay. Tomorrow we'll discuss this other thermal properties and density of states. Thank you.
Thank you, sir.
Thank you, sir.